In this example, we are asked to solve for the magnitude and direction of the shear stress that this water is applying on the bottom surface and the free surface. In this example, we are also given the velocity profile of the water, which is a parabolic velocity profile given by this formula. So let's look at the solution to this problem. Now we know that the shear stress acting on a fluid depends on its viscosity and the velocity gradient. So shear stress is given by viscosity, the dynamic viscosity times the velocity gradient du by dy. So in this case, u is basically equal to capital U times this quadratic term. And now if we just substitute this velocity in the formula for the stress, we would get the expression for the shear stress acting on the bottom plate as bottom wall as well as the top surface. So let's find out the derivative du by dy. It is equal to capital U times 2 by h, because the the derivative of this first the derivative of this first bracket term is just 1 uh, 1 by h, and then the derivative of this second bracket term is 2 times y by h square. Now, so substituting this derivative in the expression for the shear stress, we get tau yx equal to mu times capital U times 2 by h minus 2 y by h square. So this is the expression for the shear stress, but now we are asked to find the shear stress on the base and the free surface. So the base, the value of y is basically equal to 0. So tau yx at the base is tau yx, where y is equal to 0. And if you substitute y equal to 0 in this term, what you will get is tau yx to be equal to mu u divided into 2 by h minus 2 into 0 by h square. So this term becomes 0. So tau yx base is basically 2 times the viscosity times u divided by h. So this is the magnitude of the shear stress acting on the base, and this is the stress acting on the fluid due to the base. So if we zoom in near the base and if we concentrate on a fluid element which is close to the base, from a sign convention we know that positive stress acting on this fluid element uh, will be directed as shown by these arrows. So so on this fluid element, the shear stress acting due to the base at the bottom surface is directed in the negative direction. So the stress acting on the base due to the fluid will be directed in the opposite direction. That means in the positive direction. Now similarly, at the free surface, y is equal to h. And if we substitute y is equal to h in this formula, say 3. So what that will give us is mu times capital U times 2 by h minus 2 into h by h square. And if you simplify this, you will get that tau yx, the free surface, is exactly equal to 0. Yes, so basically the shear stress acting on the base due to the fluid element is 2 times the dynamic viscosity times U divided by h, and it acts in the positive x direction, while the shear stress on the free surface is exactly equal to 0.